Alright, welcome back. We'll continue with chapter 9 and the application of anti-differentiation with differential equations. Last time in 9e, we looked at solving an equation when we separate the variables, and the last example was an application kind of using flow rates. So we'll continue with this exercise with equations that will start with related rates. First we'll do example 20. It's just to review some of the rules that will be useful. So in here it's just a direct application. Now with part A, as you introduce another variable, that's when you will apply the chain rule. Okay, knowing that you have dx over dt, here we have y in terms of x, it means we can get dy over dx. And from that, using that, after we create that differential equation that had dy dt in terms of t, we'll separate the variables and try to resolve it. Okay, so you just use a direct chain rule and we get an expression of dy dt in terms of t. Now for part B, as a trick, what we do is tangent, we can express it as a quotient of sine over cos. Now remember, we're trying to anti-differentiate, and here is something that you need to scan for is when you have factors or fractions, look for on the numerator something that could be a factor as a derivative of something else. And that's what happened here is negative sine is the derivative of cos on the denominator. So this being the original function that you suspect will have a derivative here, what we do is we do a substitution. We call u equals cos of t, du over dt is negative sine of t, and with those new expression we substitute back in here. So now we get dy over dt will be negative 3 dt over u. So let me write that out before, because they jumped the gun and it just anti-differentiate. So that's equal to 3, the sine of t is coming from here. Okay, so that's gonna be du, let me rephrase that. You should have anti-differentiate in terms of dt. Yep, so that's gonna be negative sine dt equals du, so you're gonna have a negative here. Okay, and the denominator, it's going to be u. Okay, we factorize the negative 3 after we applied the integrals on the whole expression. Factorize the negative 3 outside. That is the definition when you anti-differentiate log of e of u as a modulus. We don't know the sign of it, so we just leave it as a modulus, and we substitute u by cos of t, and that's your final answer. By the way, just in case you didn't see, so here was dy over dt as I was in the way. Alright, typical of an exam or a SAC situation, you get a whole worded problem. Okay, so you have a cone, you'll know the dimension. The original height is, do we know the original height yet? No. So so h is the height in centimeters, that's the diameter, so r is the radius in centimeters. As you fill up with water, we have some information about the water. First is the flow rate at which you fill it up, which is as k liters per minute. Notice that's in liters, and here the dimensions are in centimeters. So when you convert somehow you use formulas using centimeters, the volume will be in cubic centimeters, so that liters will need to be converted. And if you don't remember, a liter is 1,000 cubic centimeters. Okay, so the height of the water, or the depth of the water, is x centimeters, and that's a variable at a given time t. We need to construct an appropriate differential equation for dx over dt, so it's the height, the rate of the depth of the water over time, and you need to solve it in terms of t. So given that initially the cone was empty, so that's an important information. So it means that x at t equals 0 will be equals 0. That will help you to determine the constant after you anti-differentiate. Okay. Probably pause here, try to set up as many equations as you can. Here, remember, it's a 3D drawing, so you need to relate to somehow to volume. Try to come up with expressions of volume and set up an appropriate differential equation. All right. So V, we're going to create a variable. So V in cubic centimeters is the volume of water at time t. Okay, now we have a flow rate which is of k liters per minute, which is equivalent to 1,000 k cubic centimeters. Now that's a flow rate, it's in a volume per minute. So what we can say now, we can set up that differential equation, which is dv over dt is equal to the inflow rate, which is 1,000 k. Now from that we can introduce dx dt by using a chain rule. So using a chain rule, we get dx over dt, it's dx over dv times dv over dt. We'll know, we'll substitute dv over dt later on. Now to find dx over dv, we can think about dv over dx, which is a reciprocal. We need to come up with a relationship between x and the volume. Okay, for a cone, you need to remember v equals a third of pi y squared times x. Now the pi y squared, we're going to define y as the radius length of the surface when the depth is x centimeters. So going back to that drawing, that's x, that y is this side. Okay, similarly, when the cone is full, that's the height, and half of it is the radius. Okay, so you need to remember your similar triangles. So let's cut the cone. Let's look at it in 2D. Let's look at half of it. That's the water. So you have a triangle x and y, and for the whole cone is h and r. Okay, we can write the ratio relationship. Now we can express y in terms of x. Now r and h are not variables, they're constants. They are the dimensions of the original cone, so we don't treat them as a variable. Now we can substitute that into the expression of v. We simplify it. Now it's an expression now in terms of x cubed. We can differentiate in terms of x, so that's a quadratic or a square. We simplify the first factor, we get the reciprocal, and we substitute that into dx over dt by using the chain rule. So it's dx over dv here and dv over dt here. We simplify and we get that expression in terms of 1 over x squared. That's constant over here. So again, I'm in the way. So here, the bottom part, that final differential equation has a constant over here, and that is all variable. So notice now we have x on the left, x on the right, dt on the right. We're going to apply the separation of variable to be able to anti-differentiate. K will be, just bear in mind that K is positive, so all of that's going to be positive. And let's move on to solving this equation. So we take the we had dx over dt. We take the reciprocal. We separate the t on the left, the x on the right. So here that's a nice antiderivative of a square. Left is t. We get a cubic plus a constant. You also know originally at t equals 0, x equals 0. So that gives us c will be is equal to 0. We get an expression of t in terms of x cubed. We make x the subject and we get a cubic root in terms of t, and that is the final solution of the differential equation. And that's it for today. See ya.